Well, hey everybody, welcome to your first calculus video. Alright, we've been doing some work with discontinuities, limits, and functional values. And I think it's time for us to kind of record some of the observations that we've made. So at this point, you can either get your own notebook paper or your spiral, but you're taking notes on your own paper. All right, and really pay attention to what's happening, what's being said here. Don't just write just to write and accomplish a task that needs to be taken care of. Really kind of try and pay attention to what we've learned and how we're going to kind of put a recording to all of that. All right, and pause the video anytime you need to, especially with all of this right here in front of you. This might be a good time to kind of stop and write it all out. All right, if you're having trouble reading my writing, because it's not the best, with this kind of approach, but I'll try and read it for you so that, there's not anything that's, not understood. Anyway, here we go. Notes, discontinuities, limits, functional values. All right, the informal definition of a limit. So if as x approaches some real number from the left and right, the f of x or the y values exist and are equal, then the limit of the function exists. All right, if we take these words and we put notation to it, it would look something like this. The left-hand limit must equal the right-hand limit. Don't forget your f of x. And those two values have to be the same. So we're going to set those two expressions equal to some number L. That's an L. Okay, I'm going to put a comma here, where C and L are real numbers. I'm hoping that our work that we've done so far makes this more understandable for you. All right, these two statements right here put together, if I did a stack of 3 dots, means therefore the limit of the function, notice this is all in the same line, as x approaches c. Notice that I don't have a superscript here. If these two limits are equal to a number and that number is the same, then we say that the limit exists and it's equal to that number L. Alright, so now we're going to look at discontinuities and limits, and then we're going to look at discontinuities and functional values. So the first topic is discontinuities and limits. Alright, so there it is, discontinuities and limits. Okay, we've seen 3 types of discontinuities. We saw a jump discontinuity, a point discontinuity, and an infinite discontinuity. And sometimes the limits exist at those discontinuities and sometimes they don't. So we're going to break it down here. So let's first of all look at where discontinuities don't exist. Or excuse me, let's first look at discontinuities where limits do not exist. I promise I'll write better than this. Just with this little stylus, it's a little bit difficult. Discontinuities where limits exist. How about where limits do not exist? Let's start with that. Let me change this up a little bit. There we go. Discontinuities where limits do not exist. D&E. All right, so let's get a graphical representation of this situation. So we're going to draw 2 graphs. We're going to call this graph f of x, this function f of x. We're going to draw a graph where we have a jump discontinuity. Maybe it's included here, but then the graph begins here again and maybe travels upward. So we know this is a jump discontinuity, and that jump discontinuity is occurring at the x value of c. All right, let's put some labels on the y-axis. I'm just going to make up some numbers, some y values. So we'll call this 1, and perhaps this is 4. All right, let's take a look at the left-hand and the right-hand limit. So the limit of the function as x approaches c from the left. As we approach c from the left, the intended height is 1. So that's our left-hand limit. Let's look at the right-hand limit. The limit of the function, and this should all be on the same line, as x approaches c from the right. Okay, as we approach c from the right, we're on this part of the graph, the intended height is 4. Because these two numbers don't equal each other, they exist, but they don't equal each number, okay, we can say that the limit does not exist. Okay, you could also write this notation this way. We could say that 1 doesn't equal 4, but we all know that. Okay, the limit of the function as x approaches c from the left does not equal the right-hand limit. And this is the notation that represents the right-hand limit. I mean, it's clear that 1 doesn't equal 4, but you're not going to want to write that down. You're going to want to write this expression right here. So at some point, we're going to ask to justify why a limit doesn't exist, and this is one of the reasons, because we have a jump discontinuity and the left limit doesn't equal the right limit, and this is the justification that we're going to use. So this is a good line right here to keep in mind. So this is going to be our justification of why a limit wouldn't exist. This is what we're going to use when we're asked to explain why or justify. Okay, but basically what this is saying is, therefore, the limit as x approaches c of the function does not exist. And it's because of this reason right up here. And remember, this is a jump discontinuity. Okay, so was that the only time that we saw that a limit did not exist? No. Okay, let's consider another function where the limit didn't exist and the type of discontinuity that we saw. Okay. I'm going to call this value c. It could be 2. We just don't know what I've labeled the tick marks with, but we're just going to call it c for right now. It very well could be 2. Let's look at this function right here that has togetherness at this vertical asymptote. Okay, let's explore the left-hand and right-hand limits. The limit of the function as x approaches c from the left. Well, we can clearly see as we approach c from the left that the y values are going to infinity. That's not a number, so we would say comma dne. Likewise, the same with the right-hand limit. Okay, even though these two limits are said to be equal because they approach the same infinity, okay, right here I'm just going to say stack of 3 dots, therefore the limit of the function as x approaches c equals infinity or equals a does not exist situation. So if you're asked to justify why this limit did not exist, actually you have it right here. This is the justification. Because you're showing somebody that you're not approaching a particular real number L, you're approaching infinity. So this is the justification for an infinite discontinuity. simply reporting either positive or negative or both infinities with the DNE would be your justification. Okay, and remember, this is an infinite discontinuity. So these are two situations where a limit would not exist. All right, well, we still haven't explored the other discontinuity, the point discontinuity, so let's look at that one. And that's going to be discontinuities where a limit does exist. So do the best you can to write nice, neat, and organized with your notes, even though mine's not coming across that way. It's just kind of challenging, like I said, with this pen. Okay, so a discontinuity where a limit exists. So I'm going to draw a graph of a point discontinuity. I'm going to call the x value of this point discontinuity C, and I'm going to give it a height of 1. So because I'm running out of this page, I'm going to come over here and I'm going to do my work because I'm not going to draw another graph. So let's explore the left hand and the right hand limit. So the limit of the function as x approaches C from the left. All right, well, the intended height is 1. The right-hand limit will be the same. Sometimes I write the limit as x approaches C and then put the f of x back up here. It doesn't matter. At some point, it's all going to be down there anyway on paper, so I won't have known how you placed it on there, whether you wrote in f of x before x approaches C or vice versa. So the right-hand limit, let me put the right hand here, the positive side, is 1. So it doesn't matter that the function's not defined at x equals C. All it matters about with the topic of limits is that our intended height from the left and the right is the same. So therefore, as the informal definition states, the limits exist from both sides and they're equal to a number. So dropping the superscript, we can say the limit exists and it's equal to 1. All right, just some additional notation as well. I'm going to kind of come up here. Okay, what might we see based on this situation? Well, here's some notation. The left-hand limit equals the right-hand limit of the function. Don't forget this. This is critical. And they're both equal to 1. So you might see it presented to you that way. If this notation is presented to you, it just means that the limit exists and it's equal to 1. It doesn't necessarily mean the function is defined, okay, at that C value. Okay, and remember, this is a point discontinuity. All right, so to wrap up this part of the notes, okay, a limit will exist at a discontinuity if that discontinuity is a point discontinuity. But in the previous two examples, a limit doesn't exist where you have a jump discontinuity or an infinite discontinuity. The last part of these notes will have us look at discontinuity and functional values, but that's going to have to be done in the next video. So I'll see you in a second.